So let's talk a little bit about how that's done, right? So you got different tiers of electric generation, right? And so you got your cheaper, cleaner, more efficient units. Okay. So typically in the power grid, the cleanest, cheapest, most efficient power, it's all going to vary. And I'm going to say, I'm going to put these up here. Okay. So this is kind of varied over the years because, typically the nuclear plants, a nuclear plant will be pretty large. So, you talk about generating units, and you'll have it's not uncommon to have generating units in the nuclear industry that are in excess of 1,000 megawatts, which is quite big. I think some in Jacksonville somewhere the average to peak power usage is somewhere around the 2 to 3,000 megawatt range. So this is quite a bit of power right here. Certainly 1,000 megawatts would power a city, 400,000 or 500,000 users probably. And again, you may go look that up on the internet and find out I'm a little bit off, but 1,000 megawatts is a big unit, So you might have this nuclear power plant, and it runs and it generates 1,000 megawatts all the time because they can always sell that power at some of the cheapest power on the grid. Coal plants tend to be pretty cheap, and a coal plant, this unit might be 650 megawatts. Sometimes they're bigger. I mean, you see at 800 or 1,000 megawatts, but somewhere around 500 or 600 megawatts for a coal plant is pretty reasonable. And then the gas plants, we're talking gas turbines here. We're talking about 150 megawatts, stuff like that. And we'll talk a little bit about gas turbines in a little while. But these days with shale gas and everything, gas plants are becoming some of the cheapest power in the grid. And so this is another interesting thing that happens in the power grid is that let's say I go build a nuclear power plant, and I'm building this plant, and so I'm borrowing money. I'm floating a 30-year bond, say, on a nuclear power plant, and I'm going out and I'm floating a bond for a couple $1 billion. And I build this coal plant or a nuclear plant rather, or I might borrow $1 billion and go build a coal plant. And again, I'm planning on paying that off over 30 years. Or gas plants tend to be cheaper, but still in the hundreds of millions of dollars that I'm borrowing here to go build a nice gas plant, a nice combined cycle gas plant. And so you make these huge capital investments, based on the assumption you're going to be able to run these plants and collect money for them and basically pay the loans on them. And the coal prices and gas prices and all that stuff have been very volatile especially over the past few years. And so there's a lot of coal plants out there that people built figuring that the coal plant was going to be the cheapest thing around, and now the gas plants are undercutting them, and so the coal plants aren't running. That's another problem that grid operators face, and that's a non-trivial problem because these are huge costs. I mean, you might still owe $500 million on your coal plant, and then you find out you're not running it at 650 megawatts all the time. That at night maybe they're taking you down to 400 megawatts because they don't need the load for what you can sell the power for. So that's the thing. Those are the things that kind of happen. In general, newer plants tend to be cleaner and more efficient. Older plants tend to be a little dirtier and a little less efficient. So, in your fleet, you've got the clean, cheap, efficient ones, and those are the ones you try and run. And if we go back to my old example, I talked about the base load, which is the lowest load you want to have to that you need to generate. And generally, that load's generated by the base, the cheaper plants. Those are the ones you run all the time. So what happens though is in your fleet, you're going to have your newer, cleaner, cheaper, better plants, and then you're going to have, older. It's usually older technology, a little dirtier. These days, even the older plants, you've probably had to put back-end equipment on it to clean them up, so they're not as dirty as they used to be, but they're not as clean as the newest stuff, and less efficient, right? So they're less efficient. And let me add something here. Expensive fuel, right? Or more expensive fuel. Because here's another thing. So cheaper fuel. here's the other thing: you go build this coal plant. Well, you might make a contract with a coal mine, and you tell this coal mine maybe they've got 20 years worth of coal, and so you say, okay, for the next 20 years, every month I'm going to buy so much coal from you, right? So you commit to a long-term contract, and they give you a pretty good price on the coal, and then you're locked in at that price. So in that case, you've tried to minimize some of your risk by locking in that price, but at the same time, when something like gas comes in and it's a little cheaper now, you've already committed to buying this coal. So maybe now you can't take advantage of the cheaper gas as much because you've got to buy this coal, you've got to buy it, and you've got to burn it. So, all things that go into the equation of operating an electric grid. We're going to talk about, so now, these are your base load, your base loaded plants. These are the ones that you do, these are the ones you run all the time. And then these are what we call peakers. Okay, so these are the ones that you start up, when your load looks like this, and then you go like that. These are your base load, and so this part is provided by your cheaper, efficient cleaner, and then this delta right here is provided by stuff that you're starting up in the afternoons, or you're running it low, really low load at night, and then cranking up in the afternoon to provide this peak. And so what happens is that this ends up being your cheaper power to produce. This ends up being your more expensive power to produce, okay? So, you have to price this into your price, and when you buy electricity from the electric company, let's say you buy electricity by the kilowatt hour. And these days, let's say in Florida, it's typical, say 12 to 14 cents per kilowatt hour that you're paying, right? Well, it might only cost like 4 cents up here to make it by the coal plant, right? Now that's just to make it at the power plant. That doesn't include, that's what the power plant's selling it into the electric grid for, or the gas plant or whatever. 4, 5, 6, 7 cents a kilowatt hour is probably where you're at here. Now some of these more expensive things, they might even be more than this. They might be, 16 to 18 cents a kilowatt hour, say. So you've got to blend this out where you're able to buy the cheaper power, mix it in with a few hours of the expensive power, and then also maintain your grid. These are all the things that you've got to work out if you're running an electric company. But the main point I'm trying to make here is that these peaks in the afternoon, these or in the morning, just depending on summer or winter, but these peaks are always provided by more expensive power, right? And so, if you can shave off some of these peaks, if there was a way that you could send information to your customers and say, hey, Mr. Customer, I'd really appreciate it if you would not run your AC quite so much in the afternoon, because that's going to prevent me from having to build a new power plant, or it's going to prevent me from having to start up this old dirty plant to supply that power for you to run that AC that afternoon. So, there's an opportunity right there. If you're a businessman, if you're an entrepreneur, there's a lot of money to be saved there. Because like I said, let's say that over time, here's your peak, and let's say your peak starts getting higher and higher. Well, eventually you're going to run out of these older inefficient units to run. You're going to get to a point where maybe this is as much as you can make, and that you're going to need to make this much next summer. And so you've got to build something. You've got to go build one of these plants that's going to require you to invest tens to hundreds of millions to billions of dollars to build it. And so, of course, the longer you can delay that, or anything that you can avoid making this huge capital investment just to meet this peak, saves you a lot of money. Okay, so there's a real economic driver to smart grid technology right there. And we'll talk a little bit about that. We'll talk some more about that in a minute. But so anyway, there's one of the problems, right? If you're running an electric grid. So let's talk about a couple of other things here. Let's see. I need to go back to where I was. Okay, so here we are in the electric grid again, and so we talked about the peak and being able to shave the peak, and I had talked about curtailable rates for an industrial customer here. So you tell the industrial customer in the afternoon, maybe he's a 10 megawatt load if it's a big plant, and you tell him, hey, I'd really like to be able to cut off that 10 megawatts in the afternoon because it's really going to help me out. There's a whole power plant that I don't have to start up and run to provide that 10 megawatts. So it's worth it to me to give you a special rate. I'm going to give you a special deal because I'm going to save a whole lot of money by not having to buy that, or not having to start up that power plant, or not having to buy that power plant, say, from one of my neighbors who might have some excess capacity. So I'm going to give you a special rate, and it'll be a win-win situation for both of us. Well, the other thing is in your residential customers, I talked about, going and reading the meter once a month. So, you read the meter and you know how much power they used over the course of the month, and you send them the electric bill every month. But what you'd really like to be able to do is to make the power in the evenings and late at night, and when your load is lower, you'd like to make that power maybe cheaper, or charge the same rate, but in the afternoons, that afternoon power, maybe you want to make that a little more expensive so that you're giving them an incentive to be more judicious in their power use. Maybe they don't need to keep the AC at 76 at 4 o'clock or 5 o'clock in the afternoon when everybody's cranking their AC. Maybe they could let it go to 78. Maybe they'd be willing to do that if it was going to save them $20 on their power bill every month. So you'd really like to be able to tell not only how much they use, but when they use it. Well, that requires some additional technology now, because you obviously can't send the guy around once a month or once an hour or every 15 minutes to go read his power meter to see how much power he's used in the afternoon. You need to automate that. So now you're going to need to put in a wireless network, and you're going to need to do automated meter reading and all that. But now maybe you can do some demand-based pricing where you can send some signals back to the house or back to the customer. You can tell them, hey, in the afternoon, maybe don't come home in the afternoon and start up your washer and dryer while everybody's running their AC, because that's going to require me to run my expensive power plant. It would be better for me if you waited till later in the afternoon when people aren't running their AC quite so much and it's cooling down a little bit. If you ran it then, it would be cheaper for all of us, and so I'll give you a better price. So it would be really nice if you could do that. So there's an economic driver right there, and some additional technology that's required. Here's another big issue for power companies, is that not all your residential customers are good about paying their power bill every month. So any electric utility has thousands to tens of thousands of customers who will wait until their power is turned off, and then they come down and pay their bill, and then you have to go out and turn their power back on, right? So the way that's typically done today and in most utilities is that you have somebody who goes out in a truck and they turn the power off, and then a few hours later when the customer scrapes up the money and goes down and pays their bill, they drive back out there and they turn the power back on. Well, you can imagine that's a tremendous expense. If you're doing that, literally tens of thousands of times a month for all these customers, you've got to have a fleet of trucks and a whole, staff of people who go out and do nothing but turn these meters off and on for the customers that don't pay their bill every month. So, it'd be really nice if you had some sort of a technology that you could just send a wireless signal and go turn their power off and then turn it back on. And some utilities are getting real inventive, because what they'll do now is they'll put in a meter for customers that have this problem. They'll put in a meter that's got a little swipe card, and so you kind of do it like a little debit card thing. You go and you put $20 on your meter, and it tells you how much money you got left, and when you're getting low, you go and you scrape up another $20 and you put another $20 in the meter. And so there's using technology to solve this problem. Now you don't need to have the people to drive out and go turn off the power and turn it back on. You've automated it. So there's an opportunity for cost savings and improving the electric grid right there. So, and the last thing I guess I want to talk about as far as the electric grid and the demand is to talk about putting in these renewable energy sources now. So, this has become a big issue now for like utilities in California, because they've been mandated to have, I believe it's 10% of their generation come from renewable energy sources. So we've talked about the demand, and I've drawn those demand curves, and so typically this is what happens: is you've got, say your nuclear plant here is capable of producing 2,000 megawatts, and so you have it producing 2,000 megawatts all the time because you're using it for your customers. Whoops. You're using it for your customers, and maybe you're also selling it to a neighbor who doesn't have a nuclear plant, but you're selling it to them cheap. So you can keep your nuclear plant base loaded, and you can pay your mortgage on your nuclear plant, right? You got to pay those bonds off. So, but you can tell it. You can tell a nuclear plant, I need you to make 1,000 megawatts, or I need you to make 2,000 megawatts, and it'll make that. And maybe every other year you take it offline for a couple of months in the spring or the fall to do maintenance on it. But for the most part, it makes power when you tell it to make power. Same thing for your coal plant. And then you have the little gas turbines. The neat thing about a gas turbine, it's like a big jet engine with a generator on it. You can push a button, and in 15 minutes you can be making 150 megawatts. So, that afternoon peak comes, and at 3 o'clock you're going to need the extra power. So you start up that gas turbine, and you start making some power. So all the traditional fossil-based generation or nuclear-based generation has the advantage that you can send a signal to that plant and tell it how much to make, and it'll make that much. And so over time, I drew those load profile curves, and power companies keep track of how much power they produce at any given time, and they run these predictive models. Maybe it's a neural network model or something, but they run these predictive models, and so they have a pretty good idea based on what time of year it is and the historical load and what the weather report says. They can make a pretty accurate estimation of what the load profile is going to look like tomorrow, and so they can load up all their generation assets, and they know to start up the coal plant and which power plants they need to run, and how many megawatts. Maybe the medium-sized power plant over here is running at 100 megawatts in the morning, and then you tell it, by the afternoon I'm going to need you to be making 400 megawatts. But it's all very deterministic, right? Well, now we start talking about these things, and they make power whenever they want to make power, and when they don't make power, you got to fire one of these things up to make up for it. So this can become a big issue, right? So let's go back and let's draw another load profile here. So here's my load profile, and let's do like a nice little summer thing here, right? So boom. So whatever I'm making here, let's just say nice round 1,000 or 1,000 megawatts, right? So my base load here is 1,000 megawatts. Well, in the old days, you would have had your coal plant and your nuclear plant making 1,000 megawatts, and but now let's say maybe you've got 100 megawatts of wind generation at night, right? But the wind generator might do something like this. So let's say the wind. Let's just say this is 0 to 100 megawatts. Let's say you've got a wind farm that'll make 100 megawatts. Well, it might do something like this. Maybe at night it's making about 70, and it does something like this, and you don't know what it's going to do. Yeah, I mean, you can kind of make some predictions based on what the weather report is and everything, but for the most part, here's 0 to 100 megawatts. It's going to do something like this, right? Same thing for your solar, right? So what happens is that at night solar doesn't make hardly anything. I mean, it might make a little tiny bit if there's a full moon or something like that, but maybe your solar generation goes down around nothing, and then in the morning it kind of goes up, and it goes up in the afternoon, and then it kind of maybe cloud banks start coming through, and it starts doing something like this, and so let's just say we've got 0 to 200 megawatts here. All right. So this is what you get from it. You can't tell it what to generate. You just get what it gives you. And then you've got this load profile that you've predicted, and so you still have to run your fossil generation. You still have to run your fossil generation to generate this, to meet this demand. And so like in this particular one, what did I say? This was my wind, right? So my wind kind of helped me out here, because it actually was generating the most at my peak, which I was just lucky. But maybe some clouds came through. Maybe it was kind of windy because there were some clouds and a little storm. But that then knocked my solar down to nothing. So all of a sudden, my solar isn't helping me out when I really need it to help out the most. So the bad thing about this is this can happen pretty quickly, and I have to have generating assets that can very quickly ramp up and generate this load now. So if I'm an electric grid operator, I've got a big problem here, right? Because here's what happens. Let's go. We're gonna talk a little bit about the different types of power plants here and how they work. So let me go up here and go to the next slide. So let's just talk about a coal plant a little bit, okay? So a coal plant, is a very simplified picture of a coal plant. But I've got coal here, okay? And I burn the coal in a furnace, and I've got a bunch of water pipes. So I generate a big fire, get it really hot, and I run water through pipes that turns to steam. And then I take the steam and I run it through a turbine. Turbine drives a generator, which makes electricity, right? So very simplified version. But here's the thing, is that this furnace and this turbine take a while to get started. I can't just flip them on and off as I need to, because I've got to burn some coal, and I got to get it hot, and I've got to run water through it, and I've got to heat the turbine up. Okay, I've got to preheat my turbine, and then I've got to get it all hot enough that I'm generating steam. And so what happens is that I can't just start and stop this plant. It might take me 8 or 10 hours to get the plant started from a cold start. And then once it gets running, I want to keep it running. The other thing that happens is let's say this is a 1,000 megawatt unit. Well, I'm going to tune this unit. The unit's designed to run most efficiently at 1,000 megawatts. Okay, so if I'm running at 800 megawatts or 500 megawatts, I'm not getting quite as good of fuel usage out of it, or fuel efficiency out of it. So it's kind of like your car, right? Your car gets gas mileage. In a power plant, we talk about heat rate. So the heat rate is the number of million BTUs, or the amount of heat you put into it, the million BTUs of heat you put into it, and then the amount of megawatts you get out of it, right? So it's megawatts per million BTU. So that's your fuel efficiency. It's like your miles per gallon. So just like your car gets the best miles per gallon when you're driving it at a steady rate on the highway, and then it gets less gas mileage, it gets less gas mileage in traffic, stop and start when you're going faster and slower and all that. Power plant's exactly the same thing. So if I'm base loaded and I'm running it at the maximum efficiency, I'm getting my best heat rate out of it. And so for every pound of coal I put in there, I'm getting the maximum amount of electricity out of it. But as I start bringing the load down, I have to put more fuel in there proportionally. I have to put more fuel out in to get the megawatts out. The other thing that happens is that as the load's moving up and down, it's harder to keep the unit tuned. So I might actually have a harder time. I might actually produce more emissions. So the emissions that we're interested in with coal plants, of course, SO2, right? Sulfur. And this is a very simplified, because what really happens, it's actually kind of interesting. I can give you an example of the St. Johns River Power Park here in Jacksonville. They built that unit in the 80s. And the total cost for 2 units that make around 1,300 megawatts was right around $1 billion. Okay, well, 400 million of that was for electric generation, actually making electricity, and 600 million of that was for emissions reduction equipment on the back end. So, the power plant, the emissions of the power plant are an important thing. And we're interested in SO2 emissions, which is from sulfur in the fuel, right? And SO2 is acid rain, makes acid rain. And I mentioned in the very beginning of this lecture that I worked for the power company and did emissions monitoring, and the SIMS, the continuous emissions monitoring systems. What we do is we actually put a little probe in the stack here, and we have a little shack down at the bottom with some computers in it and some analyzers, and we continuously measure what's coming out of this smokestack. Well, we measure the SO2, right? The sulfur that's coming out, and nitrogen oxides, NOx. Okay, that's another pollutant, and we measure the CO2, and sometimes you measure the CO, the carbon monoxide. Of course, everybody knows that this is what we're concerned about with greenhouse gases, right? And NOx is just a pollution, causes smog and stuff like that, right? So here's the deal. SO2 comes from the sulfur in the fuel. So most coal, all coal has some sulfur in it. You put it in, you burn the coal, the sulfur gets released into the flue gas. You typically, right here, you would have scrubbers that would take this out. So you have a chemical process that scrubs out this SO2 so that you have very little SO2 coming out of here, okay? NOx, nitrogen oxides, are actually produced right here in the boiler when you're burning, okay? So NOx is not... SO2 is real deterministic. If the SO2 is in the fuel, if the sulfur is in the fuel, it goes out in the flue gas. There's just no... whatever's in there goes out. It's very deterministic. So many pounds in, so many pounds out. Very easy. NOx is generated based on the combustion process. So depending on how well tuned you are here, you'll make more or less NOx. It's much more dependent on how well or how well the unit's designed and how well it's operated. And again, on the outside, we have SCRs now, selective catalytic reduction. So there would be, in between here, the boiler and the smokestack these days, there would be an SCR or some sort of ammonia injection that chemically treats the NOx and mitigates it so that there's less NOx coming out of the smokestack. And of course, CO2 is very deterministic here. You burn so many pounds of fuel, you produce so many cubic feet of CO2. Carbon monoxide, typically only a problem when the unit's starting up, but carbon monoxide is of course an issue as well. So anyway, one of the things that happens is when your load profile for this plant, if it's going up and down like this, you've got to tune the combustion process in this boiler, and you're making more specifically, more particularly NOx than SO2, but so you're making pollutants, so it's harder to keep this thing going. It's harder to keep this thing going as cleanly as possible when the load's changing. And of course, also you've got particulate emissions and opacity issues because nobody wants to see a bunch of smoke coming out of the stack. So tuning this boiler when it's following load like this becomes a little bit of an issue, and it's an operational problem for the power plant operator. But that's one of the things that happens is that you talk about the swing rate of the unit. A lot of times maybe these things can go up or down plus or minus, say, 12 megawatts a minute or something like that. 12 megawatts would be pretty high, maybe 5 megawatts a minute. It just depends on the unit and what the unit's capable of doing. But these things can only swing so much. Okay, so if you've got 2 units here, maybe you can swing 10 megawatts plus or minus a minute. So again, when your renewable generation goes up or down, the only thing you can do is to operate this power plant and swing the unit, and increase the amount of fuel. And it takes a little while, you increase the fuel and you put more heat in here and you generate more steam. And then after a couple minutes, you start generating more electricity. There's a delay. And also after you take a little heat out of here, maybe you put a little less fuel in there, but it takes a little bit for that heat to dissipate and then for your generation to go back down. So you're kind of limited in what you can do going up and down. And so, if you've got 100 megawatts of solar generation and a cloud bank comes through and you lose 50 megawatts of that pretty quickly, you're limited in what you can do with your steam units. Your ramp rate on the steam units, you're limited in what you can do to respond to that, right? So that becomes an issue. And this is something that, these are kind of new problems that we're running into in the last however many years, 10 years maybe, that we've been incorporating these renewables into the grid. We're starting to have to deal with these things. And so it's important that we be able to collect information and model and understand the problems so that we can come up with better solutions. So this is a coal plant. Nuclear plants, the same thing. You just have a nuclear reactor here instead of the coal, but these are what are known as steam units. you have a boiler, you generate steam, you run the steam through a turbine, the turbine generates turbines attached to a generator that turns and generates electricity. And so your main problem here, though, is your ramp rate. Okay, and you're limited in that. Okay, and the other thing is let's say this unit can generate 1,000 megawatts. Well, you might need to sit and hang at, say, 980 or something like that, so that if you ever need an extra 20 megawatts, you can go do it. You need a little headroom, right? So maybe you're operating it at a little less than what it's really capable of doing, just in case you need that extra 20 megawatts. You've got it. You've got some reserve. So there's a problem. There's hopefully I've explained that to you pretty well and you understand it. Next, I'm going to talk about another kind of unit, which is a gas unit, a gas turbine. So this is what a gas turbine looks like. And let me go and I'll draw on it a little bit here and hopefully make some sense of this drawing for you. So what a gas turbine is, you got the turbine part of it, the turbine generator part of it. And what it is it's really a huge jet engine with a generator on the end of it. Okay? So there's two kinds of gas turbines. They're either called gas turbines or combustion turbines. So CT and GT. Okay? So a gas turbine, big jet engine, generates power by turning the jet engine that turns the generator that makes electricity, right? So, like I said, let's say we'll talk about like a GE Frame 7. So that's a unit that you can buy, and it makes 150 megawatts. Okay? So the very cool thing about this is that you can hit a button, and in 15 minutes you can be making 150 megawatts. And actually, I've seen, I think Siemens and GE both have newer turbines now that have got this down to 7 minutes, right? Because they're trying to address this issue that I'm talking about, which is emergency generation or short-term generation when you suddenly lose some of your renewable power. Say a cloud bank comes through or the wind dies, and all of a sudden you need to make 150 megawatts really quickly. So as long as you got 7 to 15 minutes notice, depending on what model you got, you can make it up. So you've got two different kinds of these turbines, though. Okay, you've got a simple cycle, and you've got a combined cycle. And these gas turbines can typically you want to burn gas on them. They can also burn diesel. So diesel's of course very expensive. Gas these days, natural gas has gotten cheap. So a lot of times these things, if you've got a combined cycle, which is the more efficient unit, these things are some of the cheapest power in your grid now. So let's just talk about this a little bit, though. Okay, so a simple cycle is nothing but the jet engine with the generator and then the exhaust gas. Okay, so here they talk about the exhaust gas being 1,000 degrees. So these are pretty incredible machines because they can be sitting there at ambient temperature. You hit a button, they start dumping fuel into them, and in 15 minutes they're generating 1,000-degree exhaust gas. So you can imagine the thermal stresses on these things, on these blades and everything, as they go from ambient temperature up to 1,000, 1,200 degrees in 15 minutes. Thermal stresses on them have got to be just fantastic. But so anyway, you push the button, it makes power. These aren't as efficient though because the exhaust gas is coming out at 1,000 degrees. That's just waste heat. And it's just going up the smokestack, right? So you're just blowing it out the stack. But the good thing about it is it's really fast. You push the button, you make power, right? As fast as 7 minutes from 0 to 150 megawatts. So that's simple cycle. Now, the next thing is a combined cycle. Combined cycle is more efficient because now you've put this steam generator on the back of it. What you're doing is you're doing heat recovery. Okay, so heat recovery steam generator, a HRSG is what they're called. So what happens is the HRSG takes this heat, you run this 1,000-degree exhaust gas past a bunch of pipes that have water in them, and it makes steam, and you run it through a turbine, and the turbine's attached to a generator, and so you make extra electricity from this waste heat. Okay, so this, of course, makes it much more efficient. But the downside of this, of course, is that now you're no longer in this 15-minute zone. Because this all has to be prepped. You can't just start magically generating steam and driving it through the turbine real quickly. These things have to be heat soaked. They have to be brought up to temperature, because what would happen if I go generate steam and I dump it on a cold turbine, it's going to condense into water and it's going to damage the turbine. So I've lost my ability to start from nothing and be making full load, but I'm a lot more efficient now. So sometimes what you'll see is they'll have dampers on these things, and they can run them. They can just run the exhaust gas out, and they can do that pretty quickly, or they can run the whole heat steam recovery. Another thing I see them do is they'll actually run water through here to keep these things cool, and they'll just run it through a condenser if they don't need the power from the HRSG, from the steam generator. But they'll just keep the pipes cool enough that they don't melt in the exhaust gas. So, so a combined cycle can usually operate in a simple cycle. It just depends on how you want to do it. But so anyway, so these things, like, you can hit a button, you can make power very quickly, and it can help you out when your renewable generation isn't doing what you need it to do. Okay, so that's pretty cool. But here's the deal. When I hit that button and this thing is cold, it's going to generate a lot of NOx and CO and carbon monoxide and nitrogen oxides, and it's going to pollute more in the first couple of minutes of running as far as CO and nitrogen oxides go. It's going to pollute more in the first couple of minutes it runs than it will pollute the whole rest of the day after it gets heated up. So this is a disadvantage, right? So I'm running these renewables, and the whole idea of the renewable energy is that it's supposed to be very clean and it doesn't produce any pollution. But one of the side effects of it is sometimes I need to run my fossil units in a less efficient manner, and I might generate a lot more pollution than I might otherwise, because these things generate a lot of pollution when they start up and shut down. So another constraint I run into are environmental constraints, because of course this thing has a SEMS on it too. So it's got a little probe in the stack, and I've got a little analyzer that measures my NOx and CO. And I have to report that to the state, and I have certain permitted limits. So I'm usually limited in the amount of NOx and CO I'm allowed to generate in a day. And so I can't just go and start and stop this thing 5 times in a day, because I'll exceed my permitted limit. Okay, so maybe I'm limited on a unit. Maybe I can only start and stop it twice in a day because of my permit restrictions. So even though the unit's physically capable of doing what I need it to do, I might have permit and environmental restrictions that prevent me from being able to start it and stop it as many times as I might need to. So again, here we have a constraint and something that needs to be managed. So let's go back to my original slide of the electric grid here and review some of this stuff, right? And hopefully I've given you some pretty good perspective here in the last 50-something minutes, almost an hour, about why we're looking at building smart grids now. So, I've got all these problems, all these issues that I need to solve. I want to be able to do. I want to know when. I want to be able to charge customers different rates for different power, because not all power costs me the same to produce. I want to be able to give information to my customers, to my large industrial clients, and I want to be able to curtail their rates and shut off their power if I need to. I need to integrate renewable generation into my electric grid, and so renewable generation doesn't necessarily generate power exactly when I need it. Here's another problem that I didn't cover that I probably should have, is that so let's say the wind power's operating at night. Let's say I'm getting a lot of wind at night. Well, that's when my nuclear plant would be running at 1,000 megawatts. So now maybe I need to bring my power plant down from 1,000 to 950 megawatts because I got 50 megawatts of wind generation. Well, my nuke plant might not operate quite as efficiently at 950 megawatts as it did at 1,000. So I'm operating this unit a little more inefficiently to accommodate this power. And also now I'm not generating revenue at this, and I've got my bonds that I have to pay. And this was pretty expensive to put in. I got bonds to pay here too. But there's another constraint. There's another problem that I need to work on. So let's talk about smart grid and exactly what smart grid means. Okay, so smart grid is just, to me, smart grid is building the tools to solve and manage the problems that we've already discussed. Okay, so I've got, I've got user management or client management, residential client management. I want to be able to charge them different rates. I want to be able to turn on off and on their power automatically. Another thing is, let's say a storm comes through. I don't want them to have to call me to tell me their power's out. I'd rather just be able to send out a radio signal to the meter and find out that it doesn't have any power, and be able to send trouble trucks out to go fix that. I've got renewable generation that I need to manage and challenges from the renewable generation. I've got the effects on my fossil units now from the renewable generation and the fact that I have to start operating these differently. I also have environmental constraints. I can't just operate these things in any way I would like to. I have to operate them in compliance with environmental regulations and my permit restrictions. So there's another kink in my management of this system. So I've got all these problems now, and I need to collect information. Also, just the fact that the power is being fed in from different places, and my electric grid's a lot more complex. I have grid stability issues that I have to manage. I have new grid architectures that aren't completely well understood. They're fairly new, so I need to be able to collect data and analyze that. So all these problems in there together are the drivers for a smart grid. Okay, and the reason we haven't had smart grids all along is just that it's been really expensive. Like I said, when I started working for the electric company back in 1989, most of the telemetry that was collected was done over leased phone lines. The equipment was very expensive. It was very complex, difficult to install, and so you only installed it in the places where you absolutely had to have it. These days we've got computer power is cheaper, sensors are cheaper, communications are cheaper, computer equipment's cheaper, and so each one of these customers probably has a good number of the customers are going to have broadband to their house. I'm going to have wireless radio networks that I can build now that are reasonably priced. I've got satellite communications, I've got fiber optics. I've got Cisco equipment. I've got modern internet equipment, TCP/IP, all this stuff. All these newer innovations are just now starting to make themselves available on the electric grid. Electric companies have been extremely conservative, and also control systems and stuff like that. You don't upgrade them like you do computer systems. Control systems tend to be more expensive, and they also tend to require a lot of engineering effort to design and install. So, the upgrade costs are still fairly substantial, and so you might have a control system from the 90s. Well, you're still not ready to go and spend another couple $1 million to replace it. So a lot of this equipment, that's in the field is still from the early 90s to 2000 time frame. There's probably still even stuff that has been out there since the 80s. And so we're getting to the point now where we're starting to replace it with more modern equipment and take advantage of high-speed Ethernet and TCP/IP and computer power. I remember when I started working for the electric company that a 286 was the state-of-the-art processor. We hadn't even gotten into Pentiums and all that other stuff. So, literally the smartphone that I walk around with in my pocket, I couldn't have built that much computing power for $1 billion back when I started working for the electric company. And now for $500 or $600, they're making these smartphones now. Of course, you don't pay that; you subsidize it. The phone company. That's why you sign a 2-year contract, because your monthly bill is subsidizing it. But a smartphone really costs $500 or $600. But I couldn't have bought that much power for $1 billion back when I started in the power industry. And so now we've got all these new problems. We've complicated the grid. Grids are larger. People are even more dependent on electricity and reliable electricity than they ever have been in the past. And so the demands are greater, the complexity is greater, but luckily I've got all this new technology that I can start leveraging. There aren't a whole lot of people working for electric companies who understand all this technology. And again, that's why I'm so excited to teach this class and to share this stuff with you, because our country needs this, our planet needs it. We need to have more people who understand this kind of stuff. And this is all the stuff that you're going to be learning in this class. Just to give you a little preview, we're going to talk about telemetry, which is measurement at a distance, right? That's what the whole smart grid's based on, is being able to measure what's going on in the grid and bring it back. We're going to talk about instrumentation and communications. We're going to talk about how to do the system integration with computer systems, how the control systems work, electric control grids and all that, how all that stuff works. And then we're really going to talk about the computer systems that allow you to collect and analyze the data historians. So I think it's going to be a really exciting class. We're really lucky. We've got a data historian that's been donated to Palm Beach State College. And it's the data historian that pretty much every electric company in the United States and most of them in the world now are using. So it's exciting to me. I'm going to be teaching you the fundamental concepts behind all this stuff, but then I'm also going to be, you're also going to get a lot of hands-on experience with the actual tool that's going to be used by the companies that you're eventually, hopefully, going to go work for. So I'm hoping that when you get done with this, the end of this class is going to be a project where you're going to put all this stuff together and demonstrate it and do a YouTube video. And I hope that becomes part of your portfolio, that when you go in for a job interview, you're going to have this project that you've done, this nice YouTube video that's going to show off what you've learned and your skills, and that's going to set you apart from other applicants to the position and put you over the top. So I hope you're getting excited about this. I hope I did a decent job of explaining this stuff to you, and I hope it's in the unique perspective on the smart grid that's different from the other things you're going to learn. Part of this lesson, I'm going to have you're going to have to read a few things and answer some questions. But hopefully this little video, this little lecture, sets it up and gets you excited, so that you're excited to learn the future lessons and continue with this class, because I think it's a unique class, and we're very proud to be able to offer it to you at Palm Beach State College. So I hope you enjoy it, and that's the end of the first lecture.